Hello, yes, my name is Chris Gerken with Intersys Consulting out of Austin, Texas here. I'm going to talk a bit today about some powerful design patterns for Storm and Kafka, two of the key Hadoop technologies. These design patterns are applicable to the software engineering of ingestion pipelines and big data processing in general, including other runtime platforms such as MapReduce, Spark, and Tez. The focus of this presentation, however, is on Storm and Kafka specifically. Over the past 6 years, give or take, I've watched a lot of big data development projects play out, either directly as a member of the project team or vicariously through my network. Several years ago, I began to see that big data projects seem to have their own unique concerns above and beyond traditional development projects. Programmers are working with a new programming model. The team's understanding of the data will very likely change over the course of the project. The project itself needs to be much more agile than ever before, and performance becomes a key consideration far sooner in the schedule than ever before. The design patterns I'll talk about have been around for a while. Some have been with us for decades, but these design patterns stand out as even more important than before with the differences that big data brings to development projects. I'll cover those differences, not just for developers, but for other stakeholders as well, and talk about how these design patterns help mitigate the risks and technical debt brought on by those differences. Here's a list of what I call data pitfalls that exist because stakeholders are often overconfident in their understanding of the data schemas, and data stores. I'll talk in a bit about how these complicate matters for developers, but for now remember that every change in our understanding of the data will impact our application's implementation. Predictive models are derived from historical data, and their correctness is entirely dependent on how well the training set was chosen. We don't always have access to the data we want to report, so we have to come up with ways to infer those metrics from the data that we do have. In hindsight, some of those techniques turn out to have been based on opinion, not fact. When working with data that's sourced from third-party vendors, we need to be extremely vigilant as far as unexpected changes in format, volume, or protocols are concerned. And they will happen, believe me. And finally, treating a NoSQL store as if it were a relational database will not end well. It's not that we should question our data, but rather that the code we write should be as flexible as possible to withstand the changes that will certainly come along. So let's take a minute and look at the new programming model that I mentioned earlier. Applications, whether they're built on Storm, MapReduce, Spark, or Tez, are all designed in terms of a directed graph. Some platforms, like Tez, enforce a directed acyclical graph, but for now we'll talk about the more general case. With this model, nodes in the graph represent atomic business logic, and the edges represent data flows from one action to the next. Storm, MapReduce, Spark, and Tez all fit this model, but differ in the characteristics of the data flow. For example, Storm's data flow is very fine-grained, while a MapReduce data flow is very coarse-grained. As a side note, beware of anyone who makes blanket statements about which platform is better than all the others. Each data problem that we encounter is unique, and the best platform decision will vary from problem to problem. For the rest of this presentation, I'll assume for discussion's sake that Storm has been chosen as the platform for a project, and I'll describe a number of design patterns as they apply to Storm. Please understand that with minor changes, these same design patterns can be made equally applicable to MapReduce, Spark, and Tez. So let's look at this example of a directed graph implemented using Storm. This particular topology pattern is one way to address the high cost of calls to external third-party APIs. The idea is that when we make an external API call, we cache the results so that if we ever have to request that specific piece of information again, we can get it for free from our local cache instead of having to pay money to retrieve it again from the vendor. The topology is made up of 5 atomic distributable components. One of these is called a spout. It's the red one named crawler at the left of the diagram. This spout's job is to crawl some external data source and to write records, one at a time, to a stream named raw records. Streams are the mechanism by which Storm moves data from one component to the next in a topology. The other 4 components are called bolts. They're the golden ovals, or whatever that color is. And each performs one of the tasks necessary to implement the overall application. For example, the read cache bolt checks to see if the data we want to get from an external call has already been read and stored in the cache. If so, the read cache bolt enriches the record with the data in the cache and writes the record to the stream named enriched for subsequent processing by the persist bolt. Otherwise, the read cache bolt writes the record to the not in cache stream so that it can be subsequently processed by the remote call and update cache bolts sequentially. By having the 5 atomic business logic actions be built as separate standalone classes, Storm allows the application to be distributed across the cluster, able to use possibly all of the cluster's total resources, such as memory, CPU, and disk storage. In addition, Storm allows for multiple instances of each of these components, providing yet another way to scale your applications. So that's the good news. The bad news is that in order to achieve that very flexible, highly scalable application design, Storm, like MapReduce, Tez, and Spark, seems to recommend a programming practice that we've known for 25 years to be problematic, risky, and fragile, namely overloaded object-oriented implementations. Object classes tend to be at their very best when the object implements a single role, or at the very worst, a set of very closely related behaviors. We are asking the classes that implement our spouts, bolts, mappers, reduces, etc., that they implement 3 completely unrelated behaviors in this programming model. There's the behavior of playing nicely with the platform's lifecycle of events. There's the behavior of understanding the component's role in the topology, especially with respect to the collaborations with nearby components and streams. And there's the behavior of correctly performing the business logic that motivates the component's existence in the first place. It's bad enough that each of these component behaviors requires its own set of specific programming skills, some of which are very hard to find on the open market. But the data pitfalls I talked about before come back to complicate things even more. Let's say that when you get around to implementing the persist bolt, that's the one on the far right, you discover that you need some data that's available to the crawler spout on the far left, but you originally didn't think you needed those fields, so the spout didn't pass them along in the raw record stream. The fix involves modifying the shape of the records passed on every stream between the crawler spout and the persist bolt, which is all of them. Because every bolt reads and writes records that are changing, the fix will affect all components. So it's a very simple change to the topology hits almost the entire implementation. And this is actually a very common occurrence in ingestion pipelines. In fact, it will likely happen at least several times as the algorithm, made up of the components and the directed graph itself, changes during the course of the project. A storm topology will change for other reasons too. If you're implementing a predictive model with a storm topology, the topology will change as you evolve that predictive model. If you read your data from a third-party interface, you can expect to experience a total data loss, that is nothing passing through your topology, when that third party changes the format or protocol without warning, and all of the data you read fails deserialization and or parsing. As these errors are usually just logged, your first hint that there might be a problem comes when your users ask why there's no new data in the UI. It's not a fun call to get. The fix involves changing the topology to include a new component that raises an alert when the error count gets high enough. With regular changes being made to each component, and each component being heavily overloaded from an object-oriented perspective, we need to adopt several design patterns that will minimize the risk of these changes while also reducing the technical debt brought on by the object-oriented overloading. So what are these patterns? I just want to say one word to you. Just one word. Neapolitan. Neapolitan ice cream turns out to be quite analogous to the code in the storm topology. On the one hand, you have one big block of ice cream, and if you close your eyes and poke it with your finger, you can't tell where one layer ends and the next layer begins. The ingredients for each of the 3 layers turns out to be almost identical percentage-wise, but each of the 3 layers has a unique characteristic that makes them preferable to different groups of people. As I said, the implementation for storm topology is similar in many ways to the 3 layers of Neapolitan ice cream. While a developer not familiar with the storm might have trouble differentiating between the 3 layers, those layers are quite distinct and have characteristics that can be exploited to simplify the development process. Each of these layers corresponds with one of the 3 behaviors I've mentioned before. The bottom layer in this chart represents the storm-specific code you have to write in a certain way, because if you don't write the code that way, then your topology just won't work. For example, there's a method you have to implement for each spout called nextTuple. If you call the method anything else, your spout won't work. You have no say in how that method is named. The top layer represents pure business logic. This code has no knowledge of or dependency on the storm runtime environment. Unlike the code in the bottom layer, you have absolute full control over how you write this code. Because it has no storm dependency, the code in this layer can be written by anyone in your organization who A, is a competent developer, and B, understands your business. It's very difficult and expensive to find competent big data developers. If you can factor this top layer of code into a standalone library, then you can engage a developer already in your organization to write this logic, instead of trying to find and hire another developer with big data skills. Let me say that again. If you can effectively factor this top layer of code away from the other 2 layers, then you'll be able to leverage existing non-big data developers in this development work. That alone will significantly lower your development costs. The final layer is sometimes hard to spot, but it contains code that has knowledge of the topology itself. This includes the shape of data on each stream, which streams connect which components, and how records are shuffled to different tasks within the same component. Another interesting observation is the code in the bottom 2 layers can be completely generated from the minimal information you include in a whiteboard representation of the topology, something like what we were looking at a few slides ago. In fact, we have such a tool in-house. This leaves the bulk of the development to be performed by someone who doesn't really have to understand Storm. Just to be explicit about these important patterns, I'm recommending you use the helper bean pattern, in which business logic is factored away from platform-specific logic. When done correctly, this lets a business domain expert with no Storm expertise independently author and test all of the topology's business logic. The Storm-specific logic and the topology-specific logic can either be generated or hand-coded by a single developer with Storm expertise. The other pattern I want to call out involves making strongly typed interfaces between those 2 sets of code. It's these interfaces that let the business logic be both independently developed by domain experts, while also being easy to integrate with the topology-specific code by your Storm expert. Furthermore, when the topology changes, and it will frequently change, by first reflecting those changes in the strongly typed interfaces, you can make the Java compiler show you where compensating changes need to be made in the business logic. In other words, you get impact analysis for free. In short, these 2 patterns will make your development team much more efficient and responsive to changes in your business requirements and to changes in your understanding of the data, while also reducing the overall cost of that development effort. So let's take a quick look at a typical ingestion architecture. This diagram shows how stream processing can read from external sources and then filter, validate, enrich, and aggregate the data. Further batch processing can be done by MapReduce or Spark. The blue arrows indicate places where we might use Kafka if the output of one component is different than the consumption by the next component. This difference can be in terms of frequency, volume, or availability. Let's take a deeper look at Kafka and talk about some design patterns that we might use there. Probably the best way to understand what Kafka is to look at the life cycle of a Kafka message. A Kafka message is the unit of data we work with in Kafka, and it conforms to some constant format or schema within a given Kafka topic. Topics are how we categorize or distinguish between different feeds of messages. Even before a Kafka message can be created at runtime, The architect must decide what Java class will represent the message. This class can be a string for simple messages, or a specific bean class of the messages to have multiple properties. The architect also configures the topic with a message lifespan. At runtime, a Kafka message begins its life when a piece of code called a producer constructs and populates an instance of the message class. The producer serializes the message object into a byte array and passes the byte array to a Kafka server called a broker. The broker writes a message to the appropriate topic partition, causing the message data to be written to the service file system just like a commit log. If there are replicas of the partition, the brokers managing those replicas are passed the message, which then commits them to the various replicas. Once that message is committed, the clock starts ticking on the message's lifespan. Once that configured lifespan has elapsed, the message will be effectively be removed from the partition. So messages get written to the broker writes them to partitions. After some period of time, on a message-by-message basis, the messages go away. At any point in time, another piece of code called the consumer is free to access whichever messages happen to be still available in the partitions. Since the messages each have the same shelf life but have different commit times, the messages available to a client at one time are probably different than the messages available to the client at some other time. A topic may have as many consumers for as many different unique applications as you wish. So here's the same picture again, but from a Java developer's perspective. And each of these boxes represents a set of collaborating classes. The client plays two roles in this diagram. In the first role, that of message publisher, the client constructs a message object and key object and passes them to a producer. The key is only used by a partitioner to decide what partition the message is going to go to, but that key is passed all the way on through to the client. Once the producer gets a pair of encoders to serialize the key and message into a pair of byte arrays, those arrays are passed to a broker on a Kafka server for writing to a partition. And then in its role as a subscriber, the client asks the consumer for the next message. Regardless of the kind of consumer used, that consumer has ways to remember which message was last read and the means to request by partition and offset the next message. That request is sent to the appropriate broker and results in the byte arrays for the next key and message. Decoders help reconstruct the original key and object messages, the original key and message, and those are passed back to the client. Before I leave this chart, I want to make a couple of really important observations that motivate the next design pattern that I want to show you. Notice how the encoders and decoders have to be on the same page, so to speak. The algorithms used by the encoders must be the exact converse of the algorithms used by the decoders. If the key and messages are beans, then the serialization and deserialization methods are still a bit involved, but at least they're separate from the business logic, which marshals and uses the data. If the message is a string with a composite value such as XML, JSON, or tab-separated values, then extreme care must be taken during the implementation of the coders and decoders. Every time the format of the string is changed, because those two, the encoders and decoders, have to be in exact sync. The way that the topic is partitioned is another example of how the producer implementation, the consumer implementation, and the topic configuration all have to be in sync with one another. And this brings us to a commonly used Kafka anti-pattern. This is extremely common. This development and testing approach is high risk and very inefficient, yet many teams do follow this anti-pattern. The diagram shows two separate components, usually developed independently, where one component uses Kafka to get messages to the other component. As implied by the diagram, the developers for component A include in their implementation a Kafka producer that writes messages to a topic, while the developers of component B include in their implementation a Kafka consumer that reads those same messages. As a result of this arrangement, the two teams need to take great care to communicate assumptions about the configuration, such as topic name, number of partitions, server addresses, encode and decode logic, and internal format of the message and key byte arrays that get committed to the topic partitions. Any change to any one of those assumptions by one team must be carefully managed throughout design, implementation, and testing phases with the other team. Furthermore, testing is made very difficult. To test component A, it's necessary to have component B running and vice versa. It's also difficult to build a comprehensive test suite for either component. To summarize, this is risky, this is hard, this is wrong, don't do it. This picture shows the correct way to architect the use of Kafka. This implementation is almost identical to that in the previous anti-pattern, but there's one huge difference. All the code with any dependency on Kafka and any knowledge of those previous configuration or internal message format assumptions is refactored into a third component. This component encapsulates all of those intercomponent dependencies and hides them from the two original components. The team for component A still uses the producer class, but is now reusing it from the Kafka component. Likewise, component B is now reusing the consumer class from the Kafka component. Architecturally, we've turned a complex, risky, weakly typed interface into a strongly typed interface between components A and B. The successful collaboration between components A and B is no longer left to chance, as with the anti-pattern, but is now fully enforced by the compiler and version enforcement and build tools like Maven. With test, it's now very easy for each component to build scaffolding, again reusing the Kafka component, to emulate the other component's producer or consumer behavior. Now, the other component doesn't have to be running either, or even be present to complete independent testing on the components. So that brings this presentation to a close. In summary, I gave you a quick introduction to Storm and Kafka, talking about common data and coding pitfalls in big data applications, and how Storm and Kafka fit into common architectural patterns. I also described two powerful design patterns for Storm and an anti-pattern and pattern for Kafka. This really does conclude the presentation. We'll now open it up for Q&A. And as a reminder, please use the chat functions to submit your questions. Yeah, I'll give you guys a minute to type your questions in. Thanks very much for your time.